Okay, we're going to continue on with our the importance of E. And like we said in our last little video, E is really an infinite number of increases of an infinite smallness. So why is E so special? Well, we remember that when we graph exponential functions, and E is going to be a growth function because E is larger than 1. If you had a decay function like y equals 0.5, it'd be a decay function, right? It's less than 1. So as soon as you have something that's larger than 1 and you exponential function it, it's a growth function. And you got a little table kind of showing here. Is if you go e to the 0, it's 1. E to the 1 is 2.718. E cubed, right? E cubed is already up at 20. E to the 5th is 158, so it's way up here somewhere. And what we want to look at then is what's the slope on this curve. And we didn't tell you guys this, but if you ever looked at your calculator way back when, and you went to your calculator and you used to, back in math 10, go y equals, or even math 20, go y equals, and graph something, and you can go to your calculator, turn on your calculator, go to your menu, and figure out, hey, where does it cross 0 at? Hey, what's the maximum? What's the minimum? Did you know that you actually have some other properties on your calculator? If you go to your analyze graph or whatever it is, where you find zeros and maximums and minimums and intersections, it also talks about dy dx. So you can actually find the slope anywhere on a curve as well. Now, that's not a mathematical process. That's just something you can do in your calculator. So anyways, we've got the points. I got 3 points here, 0, 1, 3, all these things, 0, 1, and 3. If you ever go to your calculator and just look at the dy dx, if you said, what's the dy dx, and you put in x equals 0, it tells you the dy dx, or the slope at 0, is 1. If you say, well, do the slope, dy dx, when x is 1, the y prime is 2.718. So when x is 1, then y prime is 2.718. And if you said, well, keep going, if I put 3 into my calculator, my y prime is 20.08. And you're going, wait a minute, that's kind of neat. What if I put 5 in? If I put 5 in, the slope at 5 is 148.4. But look at all the points. They all match up. So this is the only function that you can graph where when you figure out what the point is, the y value is also the slope there. In other words, if you said, what's the slope of e to the x? Slope of e to the x is e to the x. And there's proofs for this information. And again, this one kind of deals with some limits, so it's kind of neat. But again, what they're showing on this page is that if you have a point 0 and 1, that slope at 0 and 1 has a slope of 1. They picked a point at 1, which is 2.72. That slope is 2.72. And they picked a point 2 at 7.39, and that slope is 7.39. All right, so again, and they kind of go through the limit proof in that. You can kind of see how they used some of your laws of exponents to simplify the expression. And we didn't prove e to the h minus 1 over h approaching 0. That's not a proof of ours, but you can kind of see by the graph, if you graphed e to the h minus 1 over h, is that you get this function here. So anyways, we can kind of go back, and there's lots of ways to kind of justify why the slope is what it is. But the idea is, if you've got a function, its derivative ends up being the exact same. So just again, to kind of show you that you can use your calculator to talk about a couple of different functions here. If you were graphing y equals 2 to the x and compare it to y equals e to the x. So again, when you graph e, remember, it's not a variable, it's the number 2.718. So e to the x is a steeper curve than 2 to the x because the base is larger. And again, if you were to use your calculator, and you said, hey, what's the slope on y equals 2 to the x at 3 and 8? The slope at 3 and 8 is 5.5. It kind of makes sense. This is a less steep curve, right? So the red curve is less steep than the blue curve. So the slope, when your base is less than e, the number is always going to be less than the y value, right? And then if you pick a number that's larger than e, such as 3, because 3 is larger than 2.718, If you pick a point, and here I picked 2 with 7.4 again, but on 3 to the x, 2 goes with 9 because 3 squared is 9. The slope here is 9.9. So when you think about Goldilocks and the 3 bears, and you're looking for the porridge or the chair that's just right, it's y equals e to the x is our just right base. If you pick a number less than 2.718, if you pick a base that's less than e, your slope is lower. If you pick a base that's larger than e, your slope is higher than the y values. Okay, so that's kind of the neat property of y equals e to the x. So now, how do you start taking some derivatives? Because we're all about finding derivatives, and the thing here is that if you have the derivative of a function of f of x equals e to the u, its derivative is e to the u. That's always going to be the first layer. But then the chain rule tells us that we also need to look at the derivative of the exponent. So kind of like when we did trig, we knew the derivative of a sine function is the cosine function. But if you ever had something more complicated than sine of x, you have to apply the chain rule. So the only way to kind of add some teeth or some layers to these questions is to combine e to the x with layers. So our examples then kind of demonstrate that we are always going to have some layers with our e to the x. Product rule, first function is x, second function is e to the x. Derivative of x cubed, 3x squared. Derivative of e to the x, e to the x, right? There's nothing else to that. Multiply out your product rule, and then you can see you got 3x squared, e to the x cubed, e to the x, and then what we're really going to look for is what do you have for common factoring skills. All right, so x squared is in both terms, e to the x is in both terms, so you just do some factoring. And then here's an example now where it's e, and the exponent is more than just x. It's e to the x squared. So the first layer again, all right, so we're doing a little Shrek here again. E to the x is e to the x, or e to the x squared is e to the x squared. And then you take the derivative of x squared, which is the 2x. And then now you've got the kind of the combination of a and b. You've got a product rule, and you've got a little bit messier function as well. So first function is product rule, x to the fifth. Second function is ex to the fifth. All right, so ex to the fifth starts with ex to the fifth. That's always your first layer. And what's the derivative of x to the fifth? 5x to the fourth. So then put things into your product rule, 5x to the fourth, f prime g, and then you put it in f g prime. What's common? Well, you have this ex to the fifth here, you have ex to the fifth here. So you make sure you take out your ex to the fifth. You have a 5 in the first term, you've got a 5 in the second term, so you factor out the 5. And then what do you have for exponents? X to the fourth here, so take out the x to the fourth here. All right, and that's basically what you're looking at. And then we can, again, kind of go back and use properties of functions. What's the absolute maximum value? What's the absolute minimum value? What's the region of concave up and concave down? So our first rule, again, is take the derivative. We got a product, x times e to the negative x, right? And then you can put that into the product rule, factor out e to the negative x, e to the negative x factors out. The 1 is left and the x is left, and this negative sign is left. So when we want to solve this again now for critical numbers, what makes it equal 0 or divided by 0, and what makes it top equal 0? So the top equals 0 when x is 1, and e to the x, well, if you think back to your properties of exponential functions, if you graph an exponential growth, it never hits 0, right? The range of e to the x is all larger than 0. The domain of e to the x is all reals, but the range, exponential functions, never hit 0. So the bottom is never 0. So you only have one critical number then, right? You only have a critical number of 1. So you got two things kind of happening here. Negative infinity to 1 and then 1 to infinity. You're looking at what's in the numerator. So when you pick a number that's less than 1, you go 1 minus something that's less than 1. So 1 minus 0 or 1 minus negative 2. It's a positive number. E to the x is always positive. So you know that in this first section, the first domain, that you have positive slopes, which means your function's increasing. And then the second region, when you're larger than 1, so 1 minus 2 or 1 minus 10, you get a negative number. E to the x is still positive. So now you have a negative slope, so your function is decreasing. So that means you have a maximum value going from increasing to a decreasing, maximum value of 1. If you put 1 back in the function, 1 times e to the minus 1, your maximum value is 1 over e. And then number 3 example, you've got e to the negative x squared. What is the slope? All right, so what is the slope of e to the negative x squared? Derivative of negative x squared is the 2x. So there's your slope function, and here is your sketch. All right. So yeah, lots of layers that we can add when we're doing questions that are base E. So we've got some textbook questions here for you to try as well. So good sampling of them. Again, just kind of remember that what you're looking at is sometimes just your laws of exponents you need to review. Doesn't matter if your base is E, your base is 2, your base is 10, or your base is X, right? Just watch out for your laws of exponents and then kind of simplify from there. All right, let's have some fun with some base E's.